Okay. So, oh, let me make sure I'm sharing my screen correctly with people on Zoom. 1 second here. There we go. Okay, cool. Close this right on. All right, so we're going to start off by graphing this equation x squared plus y squared equal to 25, which has what kind of shape? Not quite a parabola. If it was x squared plus y equals 25, I would agree it's a parabola. But it's a circle. A circle with a center at the origin and a radius of 5. So it looks like this. And what I really want to know is at the point 4, -3, what's the slope of the tangent line? Well, one way I could do this in this particular case is I could solve for y. It's an option here. Not always going to be an option. But in this case, we could solve for y and say, okay, y squared equals 25 minus x squared. And then take the square root of both sides. So the square root of y squared equals the square root of 25 minus x squared. But then the square root of y squared is the absolute value of y. So we really have y equal to plus or minus the square root of 25 minus x squared. So before I can figure out what the slope of the tangent line is, which I'm going to do by, wait, what am I even working on doing here? Why am I finding y? What's the whole point? What am I going to do to find the slope of the tangent line? I'm going to find a derivative. But before I can find the derivative, I felt like I needed to solve for y. Which part of the circle am I looking at here? Am I looking at the top half or the bottom half? Well, look at the bottom, right? I mean, clearly my tangent line is touching the bottom half. So I'm really looking at y equal to the negative. Instead of writing square root of 25 minus x squared, let's write 25 minus x squared to the 1/2 power. So now that we've identified the correct part, I'm going to differentiate using the chain rule. So I've got the negative of some stuff to the 1/2. My derivative, dy dx, or y prime, is the negative of 1/2 times that stuff to the negative 1/2 times what? Oh, guys, you all were so good last week. The derivative of the stuff, which is, in this case, negative 2x. And I guess we could simplify this a little bit. I don't really care that much, actually. But if I do simplify this, I get dy dx equals, let's see, the negative 1/2 and the negative 2 kind of cancel out. So I just get x, and I'm going to say, instead of times 25 minus x squared to the 1/2, divided by 25 minus x squared. I said 1/2, I meant to, instead of times 25 minus x squared to the negative 1/2, and I've divided by 25 minus x squared to the positive 1/2. And now finally, we found the derivative. Now we can plug in our x value and say that the derivative evaluated at x equal to 4 is going to be 4 over the square root of 25 minus 4 squared. 25 minus 16 is 9. The square root of 9 is 3. So my slope here is 4/3. And that looks plausible, right? The slope of this line is certainly positive, so I'm feeling okay about that. But what I'm not feeling okay about is how much work we did. We did way more work than we really needed to do. So here's the idea that we're actually working toward, is that we're going to just assume that y is some stuff, or y is a function of x. In fact, let's write it that way for just a second. Do I have enough room here? Not really. Okay, fine. So we're going to take our equation. Yeah, okay, I'm good there. Our equation x squared plus y squared equal to 25. And not that you have to do what I'm about to do, but just in this one time, let's make it easier to think of the fact that we are pretending like, or not, actually it is, we are assuming that y is some function of x. It is, right? We actually solved for y here. So we're going to say that y, let's replace y with f of x. And then instead of solving for y or f of x, we're just going to take the derivative of both sides right now. So the derivative of x squared is 2x. Let's say let's write down we're differentiating both sides. the derivative of, everybody watch, some stuff squared is going to be 2 times my stuff to the first power times, thank you so much, the derivative of the stuff, equals the derivative of 25, which is 0. And now what we're going to do is we're going to solve for the derivative. So we're going to say, well, subtract 2x from both sides. 2 times f of x times the derivative of f of x equals negative 2x. And then isolate the derivative. So divide both sides by 2f of x. So the f prime of x equals negative 2x divided by 2f of x. And I guess we could cancel an x and say that f prime of x is equal to negative x over f of x. And then we look back at our circle, which has the point x comma y, where x is 4 and f of 4 is negative 3. If I plug in x equal to 4 and f of 4 equal to negative 3, I get that my derivative, I'm trying to find a good place to write this here, that my f prime of x evaluated at the point 4 comma negative 3 is going to be exactly negative 4 over negative 3, which is positive 4/3. Just like it was before. And this is the whole idea of implicit differentiation, that we're going to assume, or that it's implied, that y is a function of x, and then we're going to take the derivative, just pretending like y is a function of x the whole time, and then at the end of the day, solve for the derivative in terms of x and y. Just so you can see how this would have worked if I hadn't done this, all we would have done is just left y alone. So if we had done this kind of the normal way, we would have just said, okay, I've got x squared plus y squared equals 25. And then we're just going to take the derivative of both sides. The derivative of x squared is 2x. We're pretending like y is a function of x. We're just not writing it as f of x. But we're going to say the derivative of y squared is 2 times y to the first times the derivative of my stuff, dy dx, or y prime, whichever notation you prefer, equals 0. And then the work is literally the same. You end up solving and you end up getting dy dx equals negative 2x over 2y, or dy dx equals negative x over y. And if you want to plug in your point, which is x equal to 4 and y equal to negative 3, you exactly get the same negative 4 over negative 3, which is positive 4/3. So that's the gist of what's going on with implicit differentiation, is that we are assuming, maybe incorrectly, but fine, that y is a function of x. And so whenever you take a derivative of some function of y, you're using the chain rule. That's the whole thing. Well, let's do some practice. Papers, okay. In fact, let's look at one of these questions on this handout here. Let's look at, say, number 41 here, where we have x times y plus y squared plus x cubed equal to 7. And we want to find dy dx. Ugh, that's terrifying. Okay, so the first step in all these, so I'll point out here, unlike the previous one, we cannot solve for y, right? Like it's really not an option. What is going on with my computer over there? Oh my God, sorry. Okay, so that's why we kind of did that first one. So we could solve for y, but here cannot solve for y, just to take the derivative of both sides straight away. So we're always differentiating first. And by the way, nowhere in this question did I write use implicit differentiation. But looking at the equation and seeing that we have all these x's and y's kind of mixed up together on one side, we should see that and be like, oh yeah, I have to use implicit. There really isn't another choice. So, oh, x times y, I'm gonna have to use the product rule there. So for the derivative of x times y, well, I'm going to do the derivative of one part. So the derivative of x is 1 times leave the other part alone, and then plus, and then switch it up. Leave the first part alone, multiply by the derivative of the second part. Okay, so here's what's going to sound like a really dumb question. Or maybe it's going to sound like a really dumb answer. What's the derivative of y? It's the derivative of y. Or if you like, you say the derivative of y is 1, and then you have to multiply by y prime. but I think it's silly to say that. Derivative of y is the derivative of y, which is y prime, or dy dx, whichever way you want to write it. Plus, now we have the derivative of some stuff squared. The derivative is 2 times my stuff to the first times the derivative of my stuff. The derivative of x cubed is 3x squared. If you're wondering why we don't say like times x prime, well, it's because we are differentiating with respect to the variable x. So if I said that, I'd be like, well, the derivative of x cubed is 3 times x squared times the derivative of x, which is 1. You can write that if you want to. It doesn't change anything. Equals not 7, but 0. The reason I say that specifically is because I've seen lots of people forget to take the derivative of the other side and just leave it as whatever constant is often over there. So make sure that you're taking the derivative of both sides, and the derivative of constants on their own are just 0. After you've done this first step, your job is to collect all the y primes on one side and put everything else on the other side. So I would leave the y primes on the left, and since they're already all on the same side, let's just factor out a y prime. Let's take it one step at a time, James. Let's leave our y primes on the left, or I should say our terms that have y prime on the left, and bring everything else to the other side. So I'm going to do negative y and a minus 3x squared. Then we would factor out y prime. That's why we want only terms with y prime on one side. So y prime times x plus 2y equals negative y minus 3x squared. And finally, divide both sides by whatever's multiplying by y prime here. So we have y prime times x plus 2y divided by x plus 2y equals negative y minus 3x squared divided by x plus 2y. And if we did more writing than I needed to there, I would have simply gone from this step straight to saying y prime equals negative y minus 3x squared divided by x plus 2y. So there is our derivative in terms of both x and y. And almost always when you're using implicit, you're always going to get your derivative in terms of x and y. It's just the way it goes. There's no better other way to do it. Questions about this before we do another one? Let's do that. All right. Let's try this next one. Let's find. So we're going to, instead of saying find the derivative, we're going to change this point a little bit, and it actually leads to a slightly different process. Find the slope of the line tangent to, what do I got here? X to the fourth plus x cubed y to the fourth plus y cubed equal to 3 at the point 1, 1. There are 2 ways to do this problem. They both start the same way. First step, if you're trying to find the slope of a tangent line, that almost always means we are trying to find a derivative. Right? Slope of the tangent line is kind of like code for take a derivative and then maybe find the slope. So let's take the derivative of both sides. Differentiating both sides. We're going to find the derivative of x to the fourth is 4x cubed. And then for x cubed times y to the fourth, we're going to have to use the product rule. So it's going to be derivative of x cubed multiplied by the not derivative of y to the fourth plus, then we switch it up. We leave the x cubed alone, multiplied by the derivative of y to the fourth, or some stuff to the fourth, which is 4 times my stuff cubed times the derivative of my stuff. You can use either dy dx or y prime. It doesn't matter what you use, just be consistent. Or don't, I mean, consistent in each problem. Right? Like I used y prime in the previous problem, I used dy dx here. It's totally fine either way. And then we still have plus the derivative of y cubed, which is 3 times my stuff squared times the derivative of my stuff equal to 0. Okay. Here is one option. This is the option that's more work. Solve for dy dx as usual. So look at these two terms that have dy dx. I'm going to leave them on the left. I'm going to simplify slightly. and write this as 4x cubed y cubed times dy dx plus 3y squared times dy. So the simplification was very slight there. I just rearranged the order of x cubed, 4, and y cubed. Equals, subtract these things from both sides, and you get negative 4x cubed minus 3x squared y to the 4th. Factor out the dy dx. You're left with dy dx times 4x cubed y cubed plus 3y squared equal to the same thing on the right. And then divide by that, so you have dy dx equal to negative 4x cubed minus 3x squared y to the 4th over 4x cubed y cubed plus 3y squared. And now that we have the derivative, we can plug in our point. So then we can say, I can put this here, dy dx evaluated at 1, 1, I'm going to get negative 4 times 1 minus 3 times 1 times 1 over 4 times 1 times 1 plus 3 times 1, which is negative 7 over 7, which is negative 1. Or, who says we have to wait to plug in the point? You can plug in the point right away. I'm going to close that door. So you all try from that step right there, plugging in the point and see what happens. If we plug in the point right away, I'm going to get 4 times 1 cubed plus 3 times 1 times 1 plus 1 times 4 times 1 times dy dx, which is 4 times dy dx, plus 3 times 1 times dy dx equal to 0. So I have, let's see, 4 plus 3 is 7. 4 times dy dx plus 3 times dy dx is also 7 dy dx. And then solving for dy dx, I get 7 dy dx equal to negative 7. So dy dx equals negative 7 over 7, which is negative 1. To me, that seems a lot easier. So if you're asked to find the slope of a tangent line for some implicit thing, you could either differentiate for, well, you should differentiate first no matter what, and you can either solve for dy dx and then plug in x and y, or first plug in x and y and then solve for dy dx. This is only true if you're trying to find the slope of a tangent line at a particular point. In the previous problem, where we were just asked to find dy dx, right, we couldn't plug in a point because there wasn't a point of tangency to look for. So this is only a good thing to do if you're being asked to find the slope of a tangent line at a particular point, not if you're being asked to find the derivative in general. But it is super nice when you're doing it this way. So either way is totally fine. Actually, I should say either way is totally fine, but obviously I think this is the better way of doing it. Okay, it's 304. All right, so that's kind of the whole gist of implicit differentiation. You got some x's and y's mixed up together, you take the derivative of the whole thing, and then at the end of the day, you solve for y prime. Let's do one more though, because there is one other thing I remember that is can be kind of dicey. Yeah, let's say, I'm just gonna make something up. Let's say we want to find dy dx for the equation. Sure. X plus 2y cubed plus 5y squared equal to sine of, yeah, gross, xy cubed. Sorry, this is gonna be kind of gnarly, but sometimes they're kind of gnarly. First things first, got to take the derivative of both sides. We're differentiating both sides. Differentiating, sure. I want to point out just the language thing here. It is incorrect to say we're deriving both sides. When you take the derivative of both sides, you are differentiating both sides. When you derive something, it's like you're figuring out it's like you're deriving a fruit. So the way that I say this, I used to say it wrong. I used to say that we are deriving both sides. We're not deriving both sides. We are differentiating both sides, or taking the derivative of both sides. Again, but also no one really cares that much. Except for me, I care a whole lot. So anyway, the derivative of some stuff cubed is 3 times our stuff squared times the derivative of the inside stuff. The derivative of x is 1. The derivative of 2y is 2 times dy dx. plus the derivative of 5y squared is 10 times our stuff to the first power times the derivative of our stuff. Oh, I don't know if I have enough room here. The derivative of sine of some stuff is cosine of the stuff multiplied by the derivative of the insides, and the derivative of the insides is going to require the product rule. It's going to be 1 times y cubed plus x times 3y squared times y prime, or 3y squared times dy dx, because they should be consistent. And that is terrible. I apologize. Gross. The reason I want to do this problem, though, is because in addition to having the usual things for an implicit differentiation, there's an extra step here. So I want to collect my dy dx's on one side. The problem here is that this dy dx is stuck inside these parentheses. They're being multiplied by this 3 times x plus 2y squared. So before I can start collecting my dy dx's on one side and everything else on the other side, I have to do some distribution. So I have to distribute this 3y squared to both the 1 and the 2 dy dx. I also have to distribute this cosine of xy cubed to the 1 times y cubed and the x times 3y squared times dy dx. It's kind of terrible. So let's be careful here. So I have 3 times x plus 2y squared times 1. So 3 times x plus 2y squared times 1. I'm not going to write the times 1. Plus 3 times x plus 2y squared times 2 times dy dx. I could simplify that. 3 times 2 to 6. Plus 10y dy dx. You might not want to write this down. It's going to be really awful. Sorry, I probably could have said that earlier. Cosine of xy cubed times y cubed. And finally, cosine of xy cubed times x times 3y squared. So 3xy squared times dy dx. Penis. Let's collect all of the dy dx's. Oh my God, there's too many of them. Not really, but there's a lot. Pick a side. I always pick the left side unless they're already all on the right side, but it doesn't actually matter. You can pick either side, totally fine. If we bring everything to the left side, we're going to have, all the dy dx's to the left side. We're going to have, let's do 3 times 2 is 6 x plus 2y squared times dy dx plus 10y times dy dx. I would generally choose to write y prime instead of dy dx. It just feels like less writing. Minus this, which I like to put the 3xy squared before the trig function. So 3xy squared times cosine of xy cubed times dy dx equal to the other stuff. So this minus that. So cosine of xy cubed times y cubed in front minus 3 times x plus 2y squared. And then we factor out the dy dx. I would love to skip this step, but I'm not going to. So I got dy dx times all of the leftovers. 6 times x plus 2y squared plus 10y minus 3xy squared times cosine of xy cubed. Good Lord. And then still equal to the same stuff over here. And then finally, so notice the tiny error I made here. That should have been cosine of x times y cubed inside the parentheses, and I accidentally put that cube on the outside of the parentheses. Let us fix that. And then we have minus 3 times x plus 2y squared. Finally, divide by all of that to get dy dx equal to this numerator, y cubed cosine of xy cubed minus 3 times x plus 2y squared, divided by that terrible denominator, 6 times x plus 2y squared plus 10y minus 3xy squared cosine of xy cubed. So they can be really gross. This is probably more gross than you will realistically see, but it's good to see something that's really gross sometimes. That's pretty much the ins and outs of implicit differentiation. We are going to have things with x's and y's. We're always making the implicit assumption that y is a function of x. So whenever you differentiate something with a y in it, you're essentially using the chain rule and saying, oh, yeah, I'm to take the derivative of my function, and then at the end of the day, multiply by the derivative of the inside, which is always going to be your y prime or your dy dx. Now, something that's cool about this is that we can use implicit differentiation to find derivatives of new functions. For example, I would love to find the derivative of y equal to the natural log of x. And there's a way of doing this. And this works especially well for functions that have nice inverse functions. So for example, in this case, we're going to say, well, I don't know how to take the derivative of y equal to the natural log of x. But if I rewrite this as e to the y equal to e to the natural log of x, which just becomes e to the y equal to x, I do know how to take the derivative of both sides of this equation. What's the derivative of e to the, so hold on, don't look there. What's the derivative of e to the x? Okay, what's the derivative of e to the stuff? Right, e to the stuff times the derivative of the stuff. So if we differentiate both sides here, on the left-hand side, we get e to the stuff times the derivative of the stuff. On the right-hand side, we get the derivative of x, which is 1. Now we're almost done. If we solve for the derivative of y, right? If y equals natural log of x, we want to find the derivative of y, which will be the derivative of the natural log of x. I'm just going to divide both sides by e to the x. So dy dx, sorry, e to the y, apologies, is 1 over e to the y. I really don't want my answer to be in terms of y. Luckily, I know what e to the y is equal to. It's literally written on the paper. What's e to the y equal to? X. So we can say, great, dy dx is equal to 1 over x. But y was equal to the natural log of x, so we're actually saying that the derivative of the natural log of x is in fact equal to 1 over x. And then immediately, now that we know a new derivative rule, we can automatically be like, hey, we also know there's a chain rule version of it. If the derivative of the natural log of x is 1 over x, then it's also true that the derivative of the natural log of some stuff is going to be 1 over the stuff times the derivative of the stuff. Always. So that means we could ask questions like, hey, what's the derivative of the natural log of x cubed minus 5x squared plus 1? And since I know the derivative of the natural log of x is 1 over x, the derivative of the natural log of some stuff is going to be 1 over all that stuff multiplied by the derivative of all that stuff, which is 3x squared minus 10x. And people often like to write this multiplied by part as the numerator. So you could write this more compactly as 3x squared minus 10x over x cubed minus 5x squared plus 1. I usually won't, because I like to think of doing my kind of my first derivative rule and just leaving the stuff as is. And then after I do that, multiplying by the derivative inside. So I like to kind of see that it's after all that, but it's totally fine to simplify like this. Cool. So now I can finally answer the question that somebody asked me before, which was number, I think, 9 on this handout. All right. Which was to find for f of x equal to the natural log of, where'd you go there? X e to the 7x to find the derivative. And I want to point out, as I've mentioned many times already, it's almost always going to be to our benefit to simplify first. We could do this the long way. We could say, okay, the derivative is going to be 1 over the stuff. And then you're going to multiply by the derivative of all that stuff, which means we're going to have to use the product and the chain rule. That's going to be 1 over x e to the 7x times, let's see, the derivative of x e to the 7x is going to be 1 times e to the 7x plus x times the derivative of e to the stuff is e to that stuff multiplied by the derivative of that stuff, which in this case is e to the 7x times 7. But then I want to point out that this really simplifies a lot. I'll show you, if we actually think about factoring out e to the 7x from the top here, we can think of this as 1 over x times e to the 7x times e to the 7x times, I'm left with a 1 plus 7x here. Feel dicey about it. No, that seems all right. Okay, yeah, I'm fine. And then we can cancel an e to the 7x here, here, and we're left with 1 plus 7x over x, or if you prefer, and I do, 1 over x plus 7. Why do I prefer that? Because if we made the smarter choice of doing the simplification first, we would have gotten to the same answer. So for logarithms, for the natural log of x e to the 7x, we can use our logarithmic rules. If you have the logarithm of a product, x times e to the 7x, you can break it up as the natural log of x plus the natural log of e to the 7x. And then the natural log of e is 1. The natural log of e to some stuff is just the stuff. So we could simplify this even further as the natural log of x plus 7x. And then, if this is our function, it is much, much less work to take the derivative now. Okay, great. My function is natural log of x plus 7x. My derivative is, the derivative of the natural log of x is 1 over x. The derivative of 7x is 7. Oh, look, it's the same answer. So I really hope this drives home the point for you that it's usually going to be a lot easier to simplify first versus differentiating without simplifying first. So take that to heart. It's really, really to your own benefit. And typically, at least when I have taught this class at other institutions, and I've asked questions like this on the first exam, I have typically asked something like, find the derivative of the natural log of something gross, like x cubed times the square root of x squared plus 1 over sine to the 4th of x times e to the x. And I've had students do it the hard way, write it as 1 over all that stuff, and then take the derivative of all that stuff using the quotient rule and the product rule twice and the chain rule at least a couple times. Not the way to do it. Not the way anyone means for you to do it. The way they mean for you to do it is to first simplify it. To write it as the derivative of the natural log of the top part, x cubed times x squared plus 1 to the 1/2 minus the natural log of the bottom part, sine to the 4th of x times e to the x. And then to break that up further as the derivative of the natural log of x cubed plus the natural log of x squared plus 1 to the 1/2 power minus the natural log of sine to the 4th of x. Careful here, minus the natural log of e to the x. If you don't like what I've done there, you can think of it as really it's minus the natural log of sine to the 4th of x plus the natural log of e to the x. Then we're going to distribute the minus sign. The way I have always seen it, sorry. Okay, the way I've always seen this is that the factors in the numerator always end up with positive coefficients. The factors in the denominator always end up with negative coefficients. That's how it always works out. So then one more simplification, and maybe two. Bring down the powers. This is going to be the derivative of 3 times natural log of x plus 1/2 times the natural log of x squared plus 1 minus 4 times the natural log of sine of x. And then minus the natural log of e to the x is just x. And now, after simplifying this quite a bit, now we are ready to take the derivative and not do nearly as much work trying to differentiate it. So now that we're actually taking the derivative, we're not going to write d dx anymore because we're actually doing what it says to do. We're going to get 3 times 1 over x plus 1/2 times 1 over x squared plus 1 times 2x minus 4 times 1 over sine of x times cosine of x minus 1. And I would not bother simplifying it, although we could. The 2 and the 2 here could cancel, and 4 times 1 over sine times cosine is really 4 times cotangent of x, because cosine x over sine x is cotangent. But don't bother. So when people talk about doing logarithmic, no, that's not the right word, James. When people talk about differentiating logarithms, usually you want to take the time to simplify the logarithmic expression if it bears simplifying. Okay, so there is, yeah. I don't imagine, so has anyone talked about the inverse tangent yet or the arctangent yet? Okay, it'll possibly come up, but I know it'll definitely come up in 17b. So you should see it now just so you know what's coming later. So we want to be able to find the derivative of the arctangent function or the inverse tangent function. So let's actually, yeah, we have 9 minutes. So let's talk about f of x equal to the inverse tangent of x, also known as f of x equal to the arctangent of x. I prefer this. Oops, you can't see anything I'm writing. Sorry. I prefer this notation because I find that it is easier to make sure I don't confuse this notation with this not actually being 1 over tangent, right? So I want to point out inverse tangent is not 1 over tangent. 1 over tangent is cotangent. Inverse tangent is a totally different animal. Inverse functions interchange the input-output rules. So for example, tangent of pi over 4 radians or 45 degrees is equal to 1, which means for us that the inverse tangent of 1 is equal to pi over 4. Or if you prefer, the arctangent of 1 is equal to pi over 4. So essentially, if tangent of an angle equals a number, the arctangent of the corresponding number equals the angle you would have taken tangent of. And in fact, when I read arctangent of root 3, for example, the words I actually say inside my head are find the angle whose tangent equals the square root of 3. So I'm looking for tangent of what equals root 3. And there is an angle that does that for us. And our angles should always be in radians, not degrees for these problems. Degree calculus works better in radians. So I know that tangent of pi over 3 radians or 60 degrees is equal to the square root of 3. So arctangent of root 3 is equal to pi over 3. Some of you might be thinking, well, James, there's actually more than one angle you could take tangent of to get root 3. And that is true. It's also true that tangent of 4 pi over 3 is equal to root 3. Well, we have a fix for that. And the fix is we've all agreed as mathematicians. Someone just decided, like, the angles you're going to have to be between negative pi over 2 and pi over 2. So the range of the arctangent function is negative pi over 2. Whoops, not with a bracket, James, with the parentheses. Because you can't ever get to negative pi over 2. Pi over 2. So just for one more example before we take the derivative of this gnarly function, if I was asking for the arctangent of negative 1 over root 3, well, here's what I know. I know that tangent of positive pi over 6 is equal to positive 1 over root 3. The nice thing about tangent here is that negative angles correspond to the same negative values. So we also know then that tangent of negative pi over 6 is equal to negative 1 over root 3. Which means that if tangent of this angle equals that number, arctangent of that number has to equal that angle. So again, tangent and inverse tangent or arctangent just interchange the role of the angle and the number. Tangent of an angle equals a number. Arctangent of a number equals an angle. Okay. But now, what we really want to do with all this is take the derivative of arctangent of x. So for f of x, I should have chosen y, equal to the arctangent of x we want to find the derivative. And we're going to do this the same way we did the logarithm. We're going to say, okay, well, let's start with y equals the arc tangent of x. I'll remind you that y is the angle and x is the number. Just like up here, right? Arctangent of the number equals the angle. Arctangent of the number equals the angle. That's equivalent to saying that tangent of the angle is equal to whatever that value is. It's very similar to what we did for the logarithm, right? We took our equation, we didn't know how to differentiate, we rewrote it so that it was now functions we recognized, and now we're going to take the derivative of both sides. The derivative of tangent of x is secant squared of x. The derivative of tangent of some stuff is going to be secant squared of my stuff times the derivative of my stuff. The derivative of x is going to be 1. Solve for y prime. So y prime is going to be 1 divided by secant squared of y. And just like last time, I'd really rather not have y's in my answer. I want, if my function is a function of x, I want the derivative to also be a function of x. There's two ways to get there. One way is to use a trig identity, which I think I've mentioned before. I think I might have said it's my favorite trig identity because it's funny. It's the tangent one. It's the I tangent gets sexy, exactly. So 1 plus tangent squared of y equals secant squared of y. So we could totally replace the secant squared of y here with 1 over 1 plus tangent squared of y. But then look, we know that tangent of y is equal to x. So tangent squared of y is equal to x squared. So our derivative here is 1 over 1 plus x squared. Alternatively, and in my opinion, preferably, you could also draw a triangle. You can say tangent of my angle y is equal to x over 1. Because I know that tangent of an angle in a right triangle is which side over which side? Oh, SOHCAHTOA. Right, so opposite over adjacent. And then the third side I can use finding the Pythagorean theorem. 1 squared plus x squared equals the remaining side squared. So the square root of 1 plus x squared is going to be whatever is over there. And then I never remember secant. I know that secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse. So cosine would be 1 over the square root of 1 plus x squared. So secant is the square root of 1 plus x squared over 1. So secant of y is the square root of 1 plus x squared over 1, which then means secant squared of y is 1 plus x squared. Exactly like we got right there. So either way you slice it, you're going to get y prime equal to 1 over 1 plus x squared. So it is important, at least if not this quarter, certainly next quarter, to know that the derivative of the arc tangent of x is equal to 1 over 1 plus x squared. And really it's important because next quarter, when you are asked to find the antiderivative of 1 over 1 plus x squared, you will need to know that it's the arctangent of x.